To graph the solution to a system of linear inequalities, we first need to graph the lines that correspond to each of our inequality statements. Those will give us the boundaries for our different regions, and then determine which region to shade, meaning which region contains the solutions, contains the coordinate points that are solutions to both inequalities. What we'll do then is first look at inequality statement 1 and solve that for y. Subtracting x to the other side will give us y equals negative x plus 2. And for our second inequality statement, we'll end up with y is equal to negative 3x plus 6. Rewriting both inequalities as equations allows us to look at these in slope-intercept form. Our first equation has a y-intercept of 2 and a slope of negative 1. So we can find our next point by going down 1, over 1, and repeating that same pattern. Since that inequality statement had that or equal to component, we'll use a straight or a solid line. For inequality 2, we have a y-intercept at 6 and a slope of negative 3, so we'll go down 1, 2, 3, and then over 1, down 3, and over 1 again. In this case, this inequality has a strict inequality statement, strictly greater than 6. So we'll use a dashed line to represent that boundary, meaning the points along that line itself aren't solutions that make our inequality statement true. Once we have our two lines graphed, we can look at choosing test points that we could plug into each of our inequality statements to see which pair makes both statements true. What we want to do is choose a point from each of our four regions. So 0, 0 would be a point we could consider. Negative 1, 5 would be a point that we could consider. Negative 4 would be a point to consider. And we could also use 5, 0. Again, this is one approach. I like it because I think it's a little bit foolproof. There are also some intuitive methods for looking at whether you should shade above or below each line. But this method should work every single time. What we would want to do then is plug each of these points into both inequality 1 and 2 to see which pair would make both inequality statements true. Rather than looking at the solutions that don't work, we're going to look at simply the solution that will end up working, which is 4, negative 4. So if we take inequality 1, we would want to plug in x equals 4 and y equals negative 4. To get 0 is less than or equal to 2, which is true. And then we would look at inequality statement 2, which would be 3 times positive 4 plus negative 4 is greater than 6, which would give us 12 minus 4, or 8, which is greater than 6. So we end up with a true statement. Since this point 4, negative 4 made both of our inequality statements true, that's the region that we want to shade. If we looked at plugging in 0, 0, negative 1, 5, or 5, 0, they would fail to make both inequality statements true, meaning those wouldn't be the regions that we want to shade as our final solution. We can apply the same idea in example 3. Turning inequality 1 into an equation and solving for y will give us y equals 3/2 x plus 10. Doing the same thing with inequality 2, we would get y is equal to negative 2/3 x plus 2. So we can start off by graphing our second line, which would have an intercept at 2 and a slope of negative 2/3. We'll graph that with a solid line, since that inequality statement is not strict. But then for equation 1, where we have our intercept at 10 and a slope of positive 3/2. I'm sorry, we wouldn't end up with an intercept of 0 there. This equation would end up being 3/2 x plus 0, not plus 10. So what we would have is our intercept starting at 0, 0, and then a slope of 3/2. So we would go up 3 over 2, up 3 over 2, and then in this case we have a strict inequality, so we'll graph that boundary with a dashed line. We can look at selecting test points, though this time around we won't be able to use 0, 0. Because our second boundary line passes through that point. We could, however, look at using 0, negative 2, negative 2, 0, 0, 3, and 3, 1 as test points to consider. So selecting one point from each of the 4 regions created by those lines. And in this case, the point that will end up working for both inequality statements will be negative 2, 0. So if we plug in 3 times negative 2 minus 2 times 0 into inequality 1, we'll get negative 6, which is definitely less than 0. So that point works for our first inequality statement. For our second inequality statement, we'll have 2 times negative 2 plus 3 times 0 which will give us negative 4, which is definitely less than or equal to 6. So that means the region containing negative 2, 0 will be in the region that we want to shade, meaning all points in this shaded region would be solutions, xy coordinate pairs that make both inequality statements true.